Have you ever tried explaining something, maybe something a bit technical to a friend, and you just feel like you're speaking completely different languages? It can be pretty frustrating.
Oh, absolutely.
Well, in a way, that's kind of what it would be like for our computers, right?
Yeah.
If they didn't have these really specific, agreed-upon rules for how to communicate.
Exactly.
And that brings us right to what you sent over, what you're curious about, getting a handle on how all these devices we use, phones, laptops, how they actually talk to each other.
Precisely. Those underlying languages, those sets of rules, we call them protocols. And yeah, this deep dive is all about protocol testing.
Okay.
We're going to unpack what that really means and, why it's so incredibly vital for pretty much everything we do: online loading, websites, streaming, you name it. We want to get a clear picture of how it all works.
Right. So our mission here is to take the info you shared, including that protocol testing tutorial focusing on layers 2 and 3, which sounds interesting,
Yeah, it's a good one.
and pull out the really key nuggets for you. The goal is for you to walk away with a solid grasp of not just what protocol testing is, but really why it matters so much in our, super connected world.
And that tutorial you sent, it's a fantastic starting point. It really dives into the nitty-gritty of how these communication rules get checked, especially at those kind of foundational network layers. So, yeah, let's jump in.
Okay, let's do it. So first things first. In the computer world, what exactly is a protocol? Break it down for us.
Okay, think of it like rules for a human conversation, shared rules.
Hmm.
If we didn't agree on, language, grammar, even basic stuff like taking turns to speak, it'd just be chaos.
Oh, chaos.
Yeah, well, computer protocols are kind of similar. They're a common set of rules, conditions that every device involved in a communication has to follow. It's an agreement.
So that's the agreement that lets my phone ask a server for a web page, and the server knows how to send it back so my phone understands it.
Exactly. Protocols handle, everything. How data gets broken into smaller pieces called packets.
Packets, right.
How those packets get addressed so they go to the right place, how they're put back together at the other end, even how errors are spotted and maybe fixed along the way. They're just fundamental for making sure data travels correctly, reliably, over networks.
Okay, fundamental. That makes sense. Which leads us straight to protocol testing. So, testing these rules, what are we actually checking?
So protocol testing, like your source points out, it's a specific way to check these protocols work correctly, and it applies across different areas: network switching, wireless, VoIP, voice calls over the internet, routing, all that stuff. The main idea, the primary goal, is to check the structure of those data packets we mentioned, the ones flying across the network. You use specialized tools to basically look inside them and make sure they're built right according to the protocol's rules.
So it's like quality control for computer conversations.
That's a great way to put it, yeah.
The tutorial mentioned using routers and switches in the testing. How do they fit in?
Right. Routers and switches, they're the basic building blocks of most networks, and they're often central to the test setup. The device you're actually testing, people will call it the DUT, the device under test.
DUT, okay.
The DUT usually talks through or connects to these routers and switches. So a big part of testing is setting up the protocols on these devices and then watching how the data flows, using those tools to see if the DUT and the network gear are following the rules correctly.
Gotcha. Now, the material you sent also talked about routed versus routing protocols. That sounds confusingly similar.
Huh. Yeah, it does sound like a bit of a tongue twister, doesn't it? But the difference is really important.
Okay.
So routed protocols are the ones that actually carry your data, the payload.
Like my email.
Or a web page. Exactly. Your emails, web traffic, video streams, that's all carried by routed protocols. IP, the Internet Protocol, is the big one everyone uses now. There used to be others like IPX or Apple Talk, but IP is dominant. Think of these as the vehicles carrying the actual cargo.
Okay, vehicles carrying the cargo. Got it. So what about routing protocols then?
Routing protocols do a different job entirely. They don't carry your data. Instead, they help routers figure out the best way to send your data.
Okay.
They're the protocols routers use to talk to each other. They exchange information about the network layout, like which paths are available, which are fastest, which are down, so they can build a kind of map. Examples are things like RIP, IGRP, EIGRP. You hear those names a lot in networking. These are more like the network's traffic signals or the GPS system.
Oh, okay. I get the analogy from the tutorial now.
Right.
The router is the bus carrying the data, routed protocol, and the routing protocols are the road signs telling the bus where to go.
Perfect analogy. That's exactly it. And different types of communication might use different protocols. And like your source mentions, big companies, Cisco, Juniper, they build all this network gear that uses tons of these protocols.
Right.
So protocol testing is basically making sure that whether it's a standard protocol like OSPF or maybe a company-specific one like Cisco's EIGRP, that it actually works the way the standard or the specification says it should.
Makes total sense. Checking they follow the blueprint. Okay, the tutorial also listed some common protocols we probably hear all the time, like TCP/IP, HTTP, FTP.
Yeah.
Can we do a quick rundown? Plain English, what do they do?
Absolutely. Let's start with the big one. TCP/IP, that's Transmission Control Protocol, Internet Protocol.
Okay.
This is really the bedrock of the Internet. TCP is the part that takes your data, breaks it into those packets, makes sure they all arrive, and puts them back in the right order. It's about reliability. IP is the part that handles the addressing and routing, getting those packets across the networks to the correct destination.
So TCP handles the reliable delivery, like making sure the whole message gets there, and IP is like the postal service figuring out the address and the route.
That's a really good way to think about it, yeah. Then you've got UDP-ICMP, User Datagram Protocol, and Internet Control Message Protocol. They also send packets over the internet, but they're different from TCP. UDP is faster because it doesn't have all the reliability checks of TCP. It's good for things like streaming video or online games where speed matters more than getting every single packet perfectly. ICMP is mostly used for error messages and diagnostics. Like if a router can't deliver a packet, it might send an ICMP message back. Think ping that uses ICMP.
Got it. Faster but less guaranteed with UDP, and ICMP is for network feedback. What about POP3 and SMTP? Email, right.
Exactly. Email. SMTP, Simple Mail Transfer Protocol, is for sending email. POP3, Post Office Protocol version 3, is one common way to retrieve email from a mail server to your email client.
Okay. Sending and receiving mail. And HTTP, I see that one everywhere in web addresses.
You do. HTTP is Hypertext Transfer Protocol. It's the protocol used to transfer web pages, the HTML files, from a web server to your browser. And your source rightly mentioned HTTPS.
A secure one.
Yeah, the S means secure. It's just HTTP with an added layer of encryption, usually SSL/TLS, to protect sensitive data like passwords or credit card numbers when you're browsing. Super important.
Definitely. Especially for online banking or shopping. Okay, last one on the list. FTP.
FTP, File Transfer Protocol. Pretty self-explanatory. It's used specifically for transferring files between computers over a network, often used for uploading website files or downloading large software installers, that kind of thing.
Okay, great. That clarifies the roles of those common acronyms we see floating around.
Mm-hmm.
Now, the tutorial also really emphasized network protocols at layers 2 and 3 of something called the OSI model. This sounds a bit more technical. Why are these layers so important?
Right, the OSI model. It stands for Open Systems Interconnection Model. It's basically a conceptual map, a way to think about the different jobs involved in network communication, broken down into 7 distinct layers.
7 layers, okay.
Yeah, but layers 2 and 3 are really, really crucial for basic network function, and that's why they're often a focus in protocol testing. Think of it like building something. You need a solid foundation and structure before you worry about the paint color. Layers 2 and 3 are like that foundation and structure for network data.
Okay, so layer 2, the data link layer. What's its job?
The data link layer, layer 2, is all about reliable data transfer between 2 devices that are directly connected on the same physical link, like 2 computers plugged into the same switch, or your laptop talking directly to your Wi-Fi router.
Directly connected, okay.
Examples here are things like MC addresses, that unique hardware address burned into every network card. Ethernet, which is the standard for wired networks. Token ring, older. Frame relay, also older. Layer 2 focuses on packaging the raw bits into frames, detecting errors on that local link, and controlling access to the shared physical medium. It's like ensuring a clean handshake between 2 neighbors.
Local delivery, the handshake.
Oh, okay.
So what about layer 3, the network layer?
Layer 3 steps up the scope. Its main job is routing data across multiple networks to get it from the original source all the way to the final destination, even if they're not directly connected. It figures out the best path through the maze of interconnected networks.
The big picture routing.
Exactly. And the key identifier at layer 3 is the IP address. If the layer 2 MAC address is like the specific apartment number in a building,
Right.
the layer 3 IP address is like the full street address, city, and zip code that lets the postal service route the letter across the country. Understanding how Layer 2 handles local delivery and Layer 3 handles the end-to-end routing is really key, because protocol testing often digs deep into making sure the protocols at these layers are working correctly, making sure both the local handshakes and the cross-country navigation are solid.
So layer 2 is getting it across the street, layer 3 is getting it across the country, roughly.
That's a good simplification, yeah.
Yeah.
It captures the difference in SCART.
Okay, so how do we actually do this testing? For these layers and others, what tools and processes are involved? The tutorial mentioned analyzers and simulators.
Right, those are two essential tool types. A protocol analyzer, sometimes called a network sniffer, is like a network detective's magnifying glass.
Okay.
It captures the traffic flowing on the network in real time or from a saved file, and then it decodes the packets. It understands the rules of hundreds of protocols, so it can show you the contents of the packets, who sent them, who received them, what protocol they're using if there are errors. It lets you see exactly what's going on.
See the raw communication. And simulators.
Simulators do something different. They pretend to be parts of the network. You can use a simulator to mimic, say, thousands of users accessing a server, or simulate a specific type of router or network condition. This is great for testing how your DUT behaves under load, or in response to specific, maybe unusual network events without needing a huge physical test lab.
So the analyzer lets you watch the real thing. The simulator lets you create specific test scenarios. Makes sense.
Exactly. And the typical testing process, you'll often have your DUT connected maybe to some switches, some routers. You configure the protocols you want to test on the DUT and maybe the supporting gear. Then you run your test, maybe generate traffic with a simulator, maybe just let it operate normally. And you use the protocol analyzer to capture and examine the packets the DUT sends and receives.
And you're checking if those packets look right, if they follow the rules.
Precisely. You're verifying the packet structure conforms to the protocol standard. Are the headers correct? Are the right flags set? Is the data formatted properly? You're checking if it's speaking the language correctly.
And what specific things are testers usually looking for? Performance, errors.
Yeah, your source mentions several key aspects. Scalability is a big one. How does it
Yeah.
handle more traffic, more users? Performance, is it fast? Is the latency low? How efficient is it? And fundamentally, the correctness of the protocol's logic, its algorithms, are they implemented right? And yeah, tools like IX Networks, which is a big commercial platform, or open source tools like Scapy and Wireshark are the workhorses here.
Okay, Scapy and Wireshark, you mentioned them, and the tutorial did too. We should definitely dig into those. But first, the tutorial also broke down protocol testing into different types of tests. Can you walk us through those?
Sure. At a high level, you're often checking sort of three main things. Correctness, are we getting the packets we expect, when we expect them? Latency, how long does it take packets to get through? And bandwidth, how many packets per second can the system handle?
Okay, correctness, delay, and speed. Pretty fundamental.
Definitely. And then your source grouped tests into stress and reliability tests and functional tests.
Right.
Stress and reliability, that's all about pushing the system. Load testing means simulating lots of normal traffic. Stress testing means pushing it beyond normal limits to see where it breaks. Performance testing measures speed, stability, responsiveness under different loads. Like, how tough is this system? Can it handle the pressure?
Testing its limits. Okay.
Yeah.
What about functional testing?
Functional testing is more about, does it do the right thing under normal or maybe slightly unusual conditions? This includes things like negative testing, deliberately feeding it bad data, or trying invalid actions like a wrong password to make sure it handles errors gracefully and securely. Then there's conformance testing. This is huge. It's checking if the way a vendor implemented a protocol actually follows the official standard, like the rules defined by the IE, or in those IETF RFC documents.
RFC's request for comments. Those are the blueprints, right?
Exactly, the blueprints for internet protocols. Conformance testing checks if the product was built according to the blueprint. And closely related is interoperability testing. This checks if devices from different vendors that supposedly follow the same standard can actually talk to each other properly.
Ah, that sounds critical. My Dell laptop needs to talk to my Netgear router.
Precisely. You usually do conformance testing first to make sure each device speaks the basic language correctly. Then you do interoperability testing to make sure they can actually have a conversation. It's vital in a multi-vendor world.
Makes perfect sense. And the tutorial also mentioned network feature testing.
Yeah, that's a bit more specific. It's about testing particular features of a network device beyond basic protocol operation. Things like port security on a switch. Does it correctly block devices trying to connect to a secured port? Or access control lists, ACLs, on a router? Do they correctly filter the traffic they're supposed to filter? You're testing against the product's own design documents for these specific features.
Checking the bells and whistles work as advertised.
Okay.
The tutorial gave some sample test cases focusing on routers. Maybe give us an example or two just to make this more concrete.
Sure. One example was one VLAN on one switch. Okay, VLANs, virtual LANs, are a way to divide a single physical switch into multiple logical networks, like virtual walls.
Right.
So this test would check if devices put into different VLANs on that switch are actually isolated. Can a device in VLAN 10 talk to a device in VLAN 20? It shouldn't, usually. So you test that the segmentation is working. Traffic stays in its own virtual room.
Okay. Checking the virtual walls are solid. Good example. What's another one?
Another good one was spanning tree, port blocking. Spanning tree protocol, or STP, is super important in Ethernet networks to prevent loops. If you accidentally connect switches in a circle, it can cause a broadcast storm and melt down the network.
Yikes. Okay.
STP's job is to detect those loops and block one of the connections to break the circle. So this test verifies that STP is doing its job correctly, identifying redundant links and blocking them, even if you have VLANs involved. They even had tests looking at how network changes affect the route path cost. That's a metric STP uses to decide which link to block. It's about ensuring network stability.
Sounds absolutely essential for preventing network meltdowns. The list also had things like telephone switch performance and negative test for device. What would those look like?
Right. The telephone switch performance test was about simulating a high call volume, like 1,000 calls at once, to see if the switch can handle it without performance dropping or calls failing. Can it keep up under pressure? And the negative test for device would be something like trying to log into the router with the wrong password multiple times. You want to verify that it correctly rejects the attempts and maybe locks the account or logs the failures following its security policy. It's testing the what if things go wrong scenarios.
And there were tests for line speed and protocol conversation rate.
Yeah, exactly. Line speed test, does the device actually push data at the speed it's rated for? If it has a 10 gigabit port, can it really handle 10 gigabits per second?
Makes sense.
Protocol conversation rate might involve watching a specific connection, say a TCP connection, and making sure the back and forth messages follow the expected pattern, like the three-way handshake to start the data transfer, the closing sequence, is it all happening correctly? And response time for session initiation, how fast does it react when you try to start something new? Like how long from when your browser asks for a web page to when the server says, okay, let's start, measuring that delay.
These examples really do help ground the concept.
Yeah.
Okay, let's circle back to those tools, Scapy and Wireshark. The tutorial seems really keen on Scapy for packet crafting. What's packet crafting?
Scapy is it's an incredibly powerful tool. Packet crafting is the perfect term. It's an interactive tool usually used with Python that lets you build network packets completely from scratch.
Build them, like piece by piece.
Totally. You can define everything. Source address, destination address, which protocols are involved, like IP, then TCP, then HTTP, set specific flags in the headers, put whatever data you want inside. You have full control over the packet's structure and content.
Wow, okay.
And it doesn't just let you build them. Scapy lets you send those custom packets onto the network, listen for the replies, and then analyze those replies, even matching them up with the packets you sent out.
So you could test how a firewall reacts to a weirdly formed packet, or see how a server responds to a specific request you build.
Exactly. It's fantastic for testing how systems handle very specific traffic, including malformed or unusual packets, which is great for security testing and protocol debugging. The tutorial mentioned other uses too, like trace routing, writing automated tests for network gear, network discovery. It's really versatile. And that little Python script example they showed.
Yeah, the one grabbing 10 packets.
Right. It just highlights how you can easily automate tasks with it, grab some packets, print a summary. Simple, but powerful.
Okay, Scapy is the builder's toolkit. What about Wireshark then? The tutorial called it an analysis tool. How does it complement Scapy?
So if Scapy is for building and sending, Wireshark is primarily for watching and understanding the traffic that's already on the network. It captures packets live or reads them from a file and displays them in a really detailed, human-readable format.
So it decodes everything for you.
It does. It knows hundreds of protocols, way more than most people ever deal with, and it can dissect the packet, showing you each layer, each header field, the data, everything. Its protocol knowledge is constantly updated too.
So Wireshark is the observer, the decoder, not so much for creating traffic.
Generally, yes. It's about deep inspection. It uses things like color coding to help you quickly spot different types of traffic or potential problems. You can set up complex filters to zero in on just the conversations you care about. As your source said, it helps you see exactly when sessions are established, when data starts flowing, how much data is sent. It gives you incredible visibility.
And it sounds like it has a lot of features.
Oh, tons. Live capture, offline analysis, really strong VoIP analysis tools, that classic three-pane view showing the packet list details and raw bytes. It runs everywhere, Windows, Mac, Linux. It can even decrypt some encrypted traffic like SSL/TLS or IPsec if you have the keys, which is essential sometimes. And yeah, you can export the data in various formats if you need to analyze it further somewhere else.
Okay, so Scapy is the precision toolkit for crafting and injecting packets. Wireshark is the superpowered microscope for observing and dissecting network traffic.
Excellent analogy. That captures the core difference perfectly.
Now, there was one more tool mentioned briefly. TTCN, Testing and Test Control Notation. That sounded different, like a language.
It is a language. TTCN, specifically TTCN3 is the current version, is a standardized testing language. It's designed specifically for writing formal test specifications and implementing test sequences, especially for testing systems that react to events, what we often call reactive systems.
Reactive system.
Yeah, systems where behavior depends on sequences of inputs and outputs over time. Most communication protocols fall into this category. A TTCN test suite is basically a collection of test cases written in this formal language.
The tutorial used a coffee machine example. How does that relate to network testing?
Right. The coffee machine is a simple way to illustrate the concept of behavioral testing. You give it an input, stimulus, insert a coin. You expect an output response, get coffee. TTCN lets you formally define these sequences. When I insert coin, then I expect coffee within 5 seconds. You can define complex sequences, alternative responses, timeouts. For network testing, instead of inserting a coin, the stimulus might be sending a specific type of packet. The expected response might be receiving a certain acknowledgement packet back from the DUT. TTCN provides a very structured way to define these interactions and automate the execution of these tests.
So it's about automating these complex stimulus response tests.
Exactly. You define the test system, the stimuli it sends, the system under test, like a router or a mobile phone, and the expected responses. TTCN includes specific elements for defining test cases, steps within a case, variables, timers to control timing, and even definitions for the structure of the data packets PDUs being exchanged.
And it seems like it's used pretty widely, not just basic internet protocols.
Oh yeah, the tutorial listed a whole range. Mobile networks like LTE, broadband, middleware, other internet protocols like SIP for voice video calls, IPv6, even smart cards, automotive systems. It shows the power of having a standardized, formal language for these complex testing jobs. Plus, it can integrate with other languages and data formats like ASN.1 or XML, which are common in telecom and networking.
Wow. Okay, so a whole different level of formalized testing there. This has been really insightful, a proper deep dive into protocol testing. It's amazing how much goes on under the hood just to make sure our devices can talk to each other reliably.
It really is a lot of complex machinery working, hopefully seamlessly.
So to kind of wrap this up, what are the main things you'd want someone listening to take away from all this?
I think the core idea is that protocols are these, fundamental rules for digital chat. And protocol testing is the absolutely essential process, can't stress that enough, that makes sure those rules are actually being followed correctly. That's what gives us the reliable, secure networks we rely on every single day. And this testing involves a whole range of techniques, from checking individual packet details to stress testing entire systems, using powerful tools like, Scapy for crafting, Wireshark for analyzing, and even formal languages like TTCN for complex scenarios.
And for you listening in, hopefully this gives you a much better appreciation for what's happening behind the screen, right? When you load a page, send an email. There's this intricate dance of protocols and testing making it all possible.
Absolutely. It's easy to take for granted, but there's a massive amount of engineering and validation involved in keeping our digital world running.
Definitely. So here's something to think about as we finish up. Considering just how complex all these communication rules are and how fast technology keeps changing, what do you think is maybe the single biggest challenge looking ahead? In ensuring our digital communications stay seamless, stay secure, keep pondering the role of those protocols and the testing that keeps them honest.